Welcome to this week's lecture in EE557. I would like to introduce you to Professor Mübeccel Demirekler. She's going to teach a few classes in this course as a guest lecturer. She's my PhD advisor, and I would like you to really enjoy this because I will. Thank you very much.
Günaydın diyerek başlıyorum. Ne zaman sunulacak bu onu bilmiyorum ama böyle başlayalım. I will talk about controlled Markov chains today. So let me write here controlled Markov chains. Okay, controlled Markov chains. And then I also would like to add here finite state. So what we're talking about, two words are important. One is controlled, the other one is finite state Markov chain. So first let us say, write what those controlled Markov chains are. I think that you know that in a controlled Markov chain we have x, okay. Ya böyle. Now, time is denoted by k, and state is denoted by x sub k at time k, and the input or the control variable is denoted by u sub k. And then we assume that the xk, which is the state, belongs to the set 1, 2, etc. up to I. So we have I number of states. And uk may be a discrete variable or a continuous variable, anything. And therefore we will represent a finite state controlled Markov chain by a transition probability matrix which will depend on the input that we have selected as P of uk. And this is nothing but something like that. P11 of uk, P1i of uk, since we have I number of states, Pi1 of uk, and Pii of uk. And then furthermore, of course, we need an initial condition, and the initial state distribution is denoted by pi 0. Now, we said that this is a controlled Markov chain, so controlling something should have a meaning. How do we control, or what do we mean by controlling, say that this Markov chain? To describe how to control, what we mean by control, we will define a cost, or sometimes a reward, doesn't make any difference. And the cost is defined as, say that the summation of incremental costs. The incremental costs is denoted by C sub k of xk uk, and on that subject we are talking about finite time horizon, so that k will start from 0 and will go up to n. Okay? So that is the thing that we have to minimize or maximize. In this course, since I'm talking about the course, we will minimize this total cost here. And now when we look at this cost, obviously this xk is a random variable, so the summation of those random variables does not make much sense. So what we have to minimize is their expected value. Expected value of the summation k from 0 to n of c sub k of xk and uk. Okay, we have to minimize this objective function there. And in some cases, equivalent problem can be written as minimize the expected value of the sum k from 0 up to n minus 1, c sub k of xk uk, and we separate the last one as c sub n of xn. The last one is usually independent of uk, but since this is, say, sort of special case of that one, so that I will talk about the first one. And indeed, this is not that much special, because usually in the final time, the input that we have used is not important because it is affecting, say, that the value of the whatever it is at time n+1, which is beyond our time horizon. Okay? Anyway, I will be starting with this expression. So that the aim is to solve that problem. Okay, this is our aim. And now, I would like to continue with the example I think that you have already studied. This is the machine example. The machine, okay. Example. In that example, we have a machine that we say rented it for maybe 3 days or n days, and then we would like to do something with this machine, of course, and the machine has two states. Either it's operating, which corresponds to xk is equal to 1, machine is operating, and xk is equal to 2, machine is not operating. Okay? And we have a control. The control is the maintenance effort. So we have 3 types of controls at any time uk. This is either 0 or 1 or 2. 0 means no maintenance. And 1 means light maintenance, and 2 means heavy maintenance. Of course, they all have some costs related with that one. And then we have to define what our, say, machine transition probability matrix of our machine is for those 3 UK values. In other words, we have to define what P of 0 is, and P of 1 is, and P of 2 is. Okay? They will be 2 by 2 matrices since we have only 2 states. In other words, I is equal to 2. And if we apply no maintenance, then we just use the probability matrix, transition matrix as 0.8, 0.2, and 0 and 1. It's obviously should be equal to 1 because that when it is not in the operating condition, it cannot come to the operating condition by itself. And for the other one, in the case of light maintenance, this is increased to 0.1, 0.9 and 0.1. And the second one is just, say, 0.4 and 0.6. And let's write the last one that we are applying a heavy maintenance there. Then in that case, we are sure that it will remain at the operating condition, so that remaining at the operating condition has a probability which is equal to 1. And when it is in the non-operating condition, then with that maintenance, we can be 90% sure that it will be in the operating condition. So that this is, say, that the model of our problem. And we also have to define, first of all, we have to define our pi 0. When we rent this machine, we assume that it is in the operating condition, so that pi 0 is equal to 1 and 0. And we also have to define what the incremental costs are. We will define the incremental costs as something like that. The incremental costs, as you can see there, is a function of the state and the input that we have applied there. The incremental costs can be written C, although I have written here C sub k, which means that it is not necessarily time invariant function. In this example, I will use a time invariant function so that we will define C of xk and uk. And that will be equal to, say that 0 if xk is equal to 0 and uk is equal to 0. That is quite reasonable because that machine is in the good condition, and furthermore, we paid nothing for the maintenance, so that the total cost is equal to 0. And we assume that the cost is equal to 5, whatever the unit is, if xk is equal to, this is not correct, I think, xk is equal to 1, xk is equal to 1, and uk is equal to 1. That is the cost of this light maintenance there. Still the machine is in the good condition, but we are applying, say, a light maintenance there so that its cost is equal to 5. And we will define the cost as 15 if xk is equal to 1 and uk is equal to 2. That means that the cost of heavy maintenance is equal to 15, and we continue in this way, say that it is equal to 20 if x is equal to 2 and u is equal to 0. So if we cannot use the machine, then we have to pay something because that we're not doing our job, and it's equal to 20. And it will continue in the same way. I mean that this will be equal to 25, and 20 plus 15 is 35. If xk is equal to 2 and uk is equal to 1 at any time, xk is equal to 2 and uk is equal to 2. So that's quite a simple reasoning here, that we define those incremental costs. And now we have almost completed our problem. The problem is to decide on a strategy or a policy which minimizes the expected cost that we have written there. Okay, so what is a policy? First of all, we have to say something about that policy. We may use very different policies. One of them is to use policy. Is to use this uk as a function, which may be a time-varying function, of xk. Such a policy is called Markov policy. We may choose another policy such that this uk is a function of xk, xk minus 1, etc., all the past states. But for this time, we just assume that it is a Markov policy, and uk is equal to g of xk. Now, we will choose a good g to minimize this expected value. How can we do that? First of all, maybe we can start with defining certain policies and then computing the corresponding costs. The policy number 1, choose uk as 0 if xk is 1, and choose uk 2 if xk is equal to 2. That is sort of reasonable. Why? Because if the machine is in the operating condition, then you don't want to pay money for the maintenance, and you just say uk is equal to 0. But on the other hand, if the machine is not operating, then you really want it to be fixed, and you just pay the high money, which corresponds to, I don't remember, this 20 here, and to make it, or 15 here, to make it in the operating condition again. Okay, so we choose this policy. This is a policy. So we can say that for that one, our uk is a function of xk, because that uk is depend on xk, and this is a time invariant function of xk. And now for that policy, we would like to calculate the corresponding cost. We will define the corresponding cost as jg, because it depends on that g here, the policy that we have selected. And jg, therefore, is defined as follows. It is the expected value of that summation k from 0 to 3. Let us say that the time horizon is equal to 3 of c sub k of xk uk. That's all. Okay? So we would like to find out that value of the objective function for such a policy there. And now to calculate this expected value, we just look at, say, this summation as the sum of the expected values. As the sum of the expected values. Now, the simple definition of expected value is just say, write this value and multiply it with the corresponding probability. And therefore, we will do exactly the same thing and write this value with the corresponding probability. But however, we will do it in a slightly different way. We have to calculate those expected values. In other words, this is only C. In other words, I will find out, first of all, C of 1 and UK, C of 2 and UK, C of 3 and UK, okay? And then multiply it with the corresponding probabilities. Multiply this one with the probability that xk is equal to 1. Multiply it with the probability that xk is equal to xk is equal to 2, and then add them together. Okay, that's what we have to do. And now I would like to write it in a slightly different way, that I want to write it as probability that xk is equal to 1 and the probability that xk is equal to 2 multiplied by that vector C of 1 UK, C of 2 UK. Okay. And we already know what our U is, because U is determined by that G here. We know that when xk is equal to 1, C of 1 UK is equal to C of 1 G of xk, G of 1, and C of 1, G of 1. Let's see what G of 1 is. When xk is equal to 1, our U is equal to 0. So it means that I will replace that one by 0, and this is our UK. And then look at this pair, the corresponding cost of this pair. The corresponding cost of this pair is xk is 1 and uk is 0. Xk is 1 and uk is 0, so that it is equal to 0. Now, let's look at the second one. C of 2 and uk. That is equal to C of 2 and uk. State is equal to 2. So this is C of 2 and G of 2. Our G function is already defined. And G of 2 gives us the value of uk as 2, because the state is equal to 2. And so that I would write it as C of 2 and 2. And look at the table and see that that is equal to 35. So whatever the value of k is, we obtain a fixed vector which is equal to 0 and 35 as our, say, ck here, independent of k. And this corresponds to the incremental cost when the state is equal to 1, and this corresponds to the incremental cost when the state is equal to, say, 2. This is our ck vector. And now we just look at this expression once more. Therefore, we can write our jg as this expected value, which is equal to, for time 0, we have, say, pi 0 here, multiplied by our c0. Remember how we have obtained the expected value by that expression. Pi 0 is the initial state distribution. And we have pi 1, and then this is not c0. Actually, this is exactly equal to c because we have the same c every time, plus pi 2 times c, plus pi 3 times c. Okay? So in this way, we can calculate the expected value of the cost. And now we have computed c, but we don't know what pi 1 and pi 2 and pi 3 are. But they are quite easy to compute because now we know the transition, probability transition matrix. And indeed, I will write here, later we will talk about again, P super G matrix, which means that we are applying the policy that we have defined there to this matrix. And how do we obtain this matrix? We just say that it will be again a 2 by 2 matrix. And it tells us that if xk is equal to 1, choose uk as 0. So we look at, say, that one. If xk is equal to 1 means that we are in the first line, so that I will copy the first row here to this PG matrix as 0.8 and 0.2. And the other part, if uk is equal to 2, if xk is equal to 2, now we will look at that matrix and copy this line, since this corresponds to the initial state being equal to, or the being equal to, say, 2, that is 0.9 and 0.1. So that this is our PG matrix, which is obtained from those, say, 3P matrices by applying the policy which we have written there. Now, obviously, it's quite easy to calculate what they are after this explanation, that this will be 1, 0 as it is given to us. And that will exactly be equal to pi 0 times PG. In our example, PG is time invariant, but it may as well be time varying. And that will be equal to pi 0 PG square. And this will be exactly equal to pi 0 PG cube. And the resultant J of G is easy to compute. Therefore, that it will be equal to pi 0 PG plus pi 0 PG C, of course, C, pi 0 PG, again something wrong, pi 0 C plus pi 0 PG C plus pi 0 PG square C plus finally pi 0 PG cube C. Okay. And J of G computed using this formula as 19.67. Now, that is one policy. We may choose some other policy. Let's say that this is policy number 2. And in that policy, we have here we use UK as 1, whatever the state is. So it's a constant function which is equal to 1 for all states. And as a result, we will generate, as we have done there, our PG matrix corresponding to this new strategy. Our G of xk is equal to 1. And this for this new PG, we just know that we are using UK as 1 for all states. So we directly choose this matrix here, 0.6, 0.9, 0.1, 0.4, and 0.6. That is our new PG, and we can calculate, this is the expected value, or the cost is same, is of course. And now in order to apply exactly the same states, we have to obtain, say that our CG, the incremental cost vector, where the first element corresponds to the state which is equal to 1, and the second element corresponds to the state which is equal to 2. And our CG for that one is equal to 5 and 25. This is equal to 5 because that's the cost of light maintenance, we just say, has written here as 5. And this is equal to 25 because that if we are in the, say, not operating condition, then we have to pay 20 extra, and the summation is equal to 25, as it is written here. And then we will use exactly the same formula, nothing will change. And for that one, we will obtain a J of G for this new strategy as, say that, 28.5, which is much larger than, of course, the result of the first strategy. And now the problem here is that how to choose the best policy or the best strategy. Now, this is our problem. But before doing that problem, we will look at the solution here, which is the computation of expected value, in a slightly different way. So that this different way, or we will try to obtain it recursively, and this recursive expression will help us to obtain, say that, the best strategy. Okay. That was just an example, and I will write, say that, the general problem here. The general problem, the model that we will use is P of U, as we have stated before. This is an I by I matrix. And we will have pi 0, which is the initial state probability distribution. And we have, okay, I will talk about something a little bit different than what we have done up to here. And however, we will not, this is just for your information. In some cases, we may have an observation related with the state, which means that sometimes we don't know the state exactly, but we have an observation. The observation at any time k may be equal to yk, and in the model we have to include the probability of this yk given that xk is equal to I, the state is equal to I from 1 to capital I. So when we state it in this way, I mean that by means of this observation here, then the controlled Markov chain, which is also a Markov decision process, now becomes, say, a partially observed Markov decision process, because that we don't know what the state exactly, but instead we just find sort of a probability related with that one. However, I will skip this part. And in our case, we have complete observation. That is called complete, not partial, but complete observation. That is at any time yk is equal to xk. So when we come to this time, then we know exactly what the state is. This is our complete observation. Furthermore, we will assume that this is one thing, and the third one here. We will assume that our uk is equal to g sub k of xk, as we have stated before. This is the Markov policy. And we have the incremental cost as c sub k of xk and uk for the time horizon k starting from 0 up to n, and xk is one of those I states, and uk belongs to some set. And then the objective function is as before. It is j, which is equal to the expected value of that summation k from 0 to n of c sub k of xk and uk. So that is our model. We will work with this model. Before minimizing this cost, we will learn how to evaluate it for a given strategy, say recursively. So here is a lemma which tells us that when a Markov policy is employed, Markov policy G is employed, the resultant state process is a Markov process. Okay, we have already used this, say, lemma there. Using this lemma means generating this PG matrix. That is what it tells us. And the proof is quite simple. Proof. That becomes a Markov process because we are using the Markov policy. Or in other words, in order to have a Markov process there, we have to look at the probability that xk plus 1g, which is, let us say that is equal to j, given all the past available states up to xkg, together with, say, u, but instead of u, I will write g of xk for k equals to 0 up to k. I'm sorry. Sorry for that one. u0 up to uk minus 1. And now this u0 is a function of x0 g, and this is a function of x k minus 1 g. Okay, so that the given condition, in the given condition, we have those random variables and their functions. Since their functions contain less information compared with those, say, random variables there, we can omit them. Okay, and the result becomes p of xk plus 1g is equal to j given x0g to xkg. But however, since this is a say Markov process, we can write it as p xk plus 1g given only xkg. That's enough. So it is, therefore the new process is also a Markov process. Note one-step transition. Probabilities are given by Pg of xk plus 1 G is equal to J, given that xk is equal to I and uk, this is equal to P, the original P matrix going from I to J, but it depends on U, and our uk is just a function of xk, which is exactly equal to I. Okay, so in this way we can calculate the say one-step transition probabilities. And note 2, m-step transition probabilities they are given as Pg of u or g of x is given as I'm sorry, P okay, I will explain in a minute. Pkg, Pk minus 1, k plus 1 g, up to p k plus 1 k plus m minus 1 g. So that this is the multiplication of all those p matrices in the time interval starting from k up to say k plus m minus 1. Okay? Although we have solved this example and what we know by that cost here, I will write it for the general case. Cost of a Markov policy. But now it's quite simple to write the cost of this Markov policy because that we have already derived lots of expressions there, and this Jg, which is the expected value of that summation k from 0 to n, and c sub k of xk uk, g of xk actually, since this is a Markov policy, is obtained as k from 0 to n up to n. Okay, so that this is the expected cost for the general case, and the aim, as I said before, is to obtain this overall cost recursively because it will help us in the optimization part of it. recursive computation of the cost. Okay, for that one we will define a concept which is called cost to go. The cost to go concept is something like that. We have a timeline here. This is the final time n, and say that the current time is equal to k. And the cost to go is to obtain the cost on that interval. And this is the time which is equal to 0. When we come to that, we will apply a backwards recursion, and we will start from the final point, and then compute this cost to go, and then decrease the value of k up to 0. When we come to the time which is equal to 0, we will obtain the whole value of the cost. That is what we have to do. And then furthermore, at any time k, we will assume that state k at that time is equal to I. So we will start with this assumption. Of course, vary this I from 1 to, say, capital I there. So we will calculate all those cost to goes. Artık yapamayacağım. All those cost to goes recursively, starting from the final time and going towards the initial time. So let us start with the final time. So we will compute V sub n g. I call it V because of some reason. Later we will call the optimal cost by the name J. And V sub n g of I. That means that at time n, this is the time, the final time. This is the state number. State is equal to I. And we will compute, say that this cost for a given policy, which is equal to G. And therefore, that will exactly be equal to, so simple, C sub n of state is I, and the input is Gn of I. That's simple for that time. And we just said that we will do it for all states. And as a result, we will obtain a vector of size n. And therefore, I will write Vng to denote this vector, okay? The elements of this vector is Vng of 1 up to Vng of capital I, number of states, which is equal to Cn of 1, Gn of 1, up to Cn of I, Gn of I. So for the, say, final time, we have computed the cost to go for each I. In other words, we have computed this cost to go vector there. Now, let us look at the time t is equal to, or k is equal to n minus 1 now. When k is equal to n minus 1, we will write this v sub n minus 1 g of I as that the expected value of that c sub n minus 1 of c sub n minus 1 of x n minus 1 and g n minus 1 of x n minus 1 plus c sub n of xn and gn of xn. So it is the sum of those two terms, but we have an extra information that the state is equal to I. So I just write it as when the state is equal to I at time n minus 1, we will calculate this expected value as our cost to go from the time n minus 1 to the final time, which is equal to n. And now that will be equal to, let us try to calculate this expected value. I think that the first one is easy because that the state value is already given. So it is a constant and it is exactly equal to C sub n minus 1 of I and Gn minus 1 of I. That is the first term. But we have to work a little bit with the second term. The second term is the expected value of that, say, C sub n of xn, G sub n of xn, given that not xn, but xn minus 1 is equal to I. Okay. Now, to calculate this expected value, we will use the fact, something like that, the expected value of x given y and z, and we take one more expectation of, say, given z is exactly equal to the expected value of x given z. Okay, we will use this fact to calculate the expected value there.